Using machine learning to predict water shortages in a city. Scenario overview. A city in a dry region is experiencing severe water shortages, and the government wants to use machine learning to predict when and where these shortages are likely to occur. By analyzing data such as daily water consumption, rainfall, temperature, and population growth over the past 5 years, the goal is to create a machine learning model that can help the city manage water resources more effectively. Task 1. Determine relevant data for predicting water shortages. To predict water shortages, the following data will be most relevant. Rainfall. Rainfall is directly related to water supply. A reduction in rainfall may lead to lower water availability, making it a critical factor in predicting shortages. Population growth. As population increases, the demand for water rises. Tracking population growth helps understand how the demand for water will change over time. Daily water usage. Water consumption patterns provide insight into how much water is being used by households, businesses, and industries. This data helps identify periods of high demand, which could lead to shortages. Temperature. Higher temperatures can increase water usage, particularly in agriculture and for personal consumption. Temperature data is also essential for understanding seasonal variations in water demand. Conclusion. Rainfall, population growth, daily water usage, and temperature are the most relevant data points for predicting water shortages. These factors affect both the supply and demand for water in the city. Task 2. Supervised versus unsupervised learning. Supervised learning. For this scenario, supervised learning is the best approach. Supervised learning involves using labeled data, i.e., historical data where the outcome, whether or not a water shortage occurred, is known, to train the machine learning model. The model can learn from the data and make predictions about future water shortages. Why supervised learning? Historical data. The city has collected data over the past 5 years, including rainfall, water usage, and population growth. This data can be used to label instances of water shortages and teach the model to recognize patterns leading to shortages. Prediction. Since the goal is to predict when and where water shortages are likely to occur, supervised learning is ideal because it can predict future outcomes based on past patterns. Unsupervised learning, on the other hand, would be less effective because it's typically used for identifying patterns in data without labeled outcomes. Example: clustering similar data points. In this case, we already know the outcomes, water shortages. So supervised learning is the better choice. Task 3. Challenges and improving model accuracy. Challenges. Unexpected population growth. If population growth suddenly spikes, the model may not accurately predict water shortages because it is based on historical data. Unexpected increases in population can lead to higher water demand than anticipated. Solution. Continuously update the model with real-time population data. The city can collect updated census data and adjust the model to account for rapid population changes. Weather changes, climate change, or unexpected weather events, example droughts, floods, could cause unusual patterns in rainfall and temperature that the model hasn't encountered before. Solution. Integrate weather forecasting data into the model to account for short-term and long-term weather patterns. Additionally, the model should be retrained periodically to adapt to changing climate conditions. Water usage variability. Water usage can vary significantly depending on the season, public policies, example water restrictions, and economic activities. These variations can make predictions less reliable if the model doesn't account for them. Solution. Include seasonality and policy changes as variables in the model to improve its ability to predict water shortages during different times of the year. Improving model accuracy, data collection and pre-processing. Ensure high-quality data by cleaning the dataset, removing outliers, and filling in missing values. Accurate data improves model performance. Model retraining. Regularly retrain the model using updated data to ensure it adapts to changes in population, climate, and water usage patterns. Feature engineering: create additional features such as rate of population growth or rainfall deviation from average to give the model more insight into the factors affecting water shortages. Task 4: ethical concerns and use of predictions. How the city should use predictions. Proactive water management: the city can use the predictions to implement proactive measures such as introducing water-saving policies, limiting non-essential water usage during peak demand periods, and investing in alternative water sources, example, desalination or recycled water. Before a shortage occurs, efficient resource allocation: the city can prioritize water distribution to critical sectors, example, hospitals, schools, during predicted shortages and ensure water is available where it is needed most. Public awareness campaigns: educating the public about upcoming water shortages and encouraging water conservation can help manage demand and reduce the impact of shortages. Ethical concerns: equitable access to water. There is an ethical responsibility to ensure that predictions do not lead to unfair allocation of water resources. Water is a basic human right, and policies based on predictions must ensure that all residents, regardless of socioeconomic status, have access to sufficient water. Privacy concerns: if the city uses personal data, example, household water usage, it must ensure that data privacy is maintained. Individual data should be anonymized to prevent misuse or exploitation of personal information. Data bias: the model may have biases if the historical data reflects unequal water distribution. The city must ensure that the machine learning model doesn't perpetuate existing inequalities or fail to account for underserved populations. Conclusion: using machine learning to predict water shortages can significantly improve the city's ability to manage its water resources. By focusing on relevant data like rainfall, population growth, and water usage, and employing supervised learning, the city can develop a model to predict and prevent water shortages. However, challenges such as unexpected population growth and climate changes must be addressed to ensure the model remains accurate. Ethical considerations, including equitable water access and data privacy, must also be taken into account to ensure responsible management of public resources.